Hi, I'm Gabriele Berton and I'm going to present the paper Deep Visual Geolocalization Benchmark. This work focuses on the task of visual geolocalization, also called visual place recognition or image-based localization, which is the task of finding the location where a given photo was taken. This is commonly approached through image retrieval, where given a large database of images with GPS coordinates, the goal is to find the most similar match to the query. Visual geolocalization can have many purposes, like autonomous driving and assistive devices. We started this work to overcome two limitations in current literature. The first is that evaluation is focused on a single metric. Most works focus only on the recall, ignoring factors such as execution time, hardware requirements, and scalability, which are crucial for the application of a method in the real world. The second limitation is a lack of a standardized framework for training models. For example, methods that use different setups, such as backbones or training dataset, are often directly compared, making it difficult to understand why a method cannot perform another one. To address these issues, we introduce a benchmarking framework. In our experiments, we do not just compare results based on the recall, which is the percentage of queries with at least one of the first n predictions within 25 meters, but we also consider practical constraints such as the GPU memories and computational costs like latency and flops. Visual geolocalization is commonly trained using this pipeline. The moving components here are colored in blue. For time constraints, I'm not going to talk about all these modules, but in our paper we carefully investigated the influence of each component with quantitative experiments. To ensure that the results are relevant for a wide range of applications, we trained and tested on multiple datasets with very diverse characteristics. Here you can see for each dataset the geographical map and an example of query and database image. Now let's move to some findings. First, we analyzed the importance of the backbone. We found that the little used compact convolutional transformer performs competitively while being fast, lightweight, and robust with both low and high dimensional descriptors, as you can see in the two plots with results on two datasets. Next analysis is related to negative mining. We found that mining is crucial and that a non-exhaustive mining can perform just as well as full database mining at a fraction of the cost. Third results are on using efficient KNN algorithms. We show that an approximate KNN can have a huge impact on time and memory footprint, with little impact on the performance. In this plot, we can see that a method like inverted file index with product quantization achieves a speedup and memory saving of 2 orders of magnitude, with a drop of 5 points in recall. Finally, some results on changing the image's resolution. We found that in some cases, lower resolutions can actually achieve higher results at lower costs, especially if there is a large domain gap between train and test set. For example, here you see methods trained on PITS 30K and tested on San Lucia, and we can see how even the recall benefits from using smaller images. This is likely due to a large domain gap between train and test sets. Finally, we show that with some careful design choices, simple architecture can reach competitive results with most recent methods. In this example, by changing a few components, we can improve not only the recall, but we can also reduce latency, training time, GPU and CPU memory requirements. So to summarize, our work brings two main contributions. It gains insights into how components impact the results and computational requirements, and it establishes a systematic evaluation protocol for comparing different results. All the code is open source. Results are fully reproducible and are averaged over multiple rounds. So thank you for your attention, and we hope to see you at the poster session 2.1.